Lesson 109, intersection of two planes. In this lesson, we are going to examine how planes can intersect. So if we consider a pair of planes, or take two sheets of paper in front of you, how can they intersect or not intersect, really, right? So if you have two pieces of paper or two planes, right, and they can be parallel and they don't intersect at all, so there are no solutions. The two pieces of paper can be right on top of each other, like they're identical. So we can have coincidental planes that gives us infinite number of solutions. Or when the two planes are not parallel to each other, then they will, of course, somehow intersect along a single line, forming infinite number of solutions also. Here is example 1. Find the vector equation of the line of intersection of pi 1 and pi 2. So first of all, notice how these two planes are written in Cartesian form. So the first thing that I can compare are their normal vectors. So n1 is 1, 2, negative 4. And n2 is 2, negative 2, and negative 5. Obviously, I cannot write these two normals as scalar multiples of each other. This implies that the planes are not parallel. All right. So that means they must intersect at a line. So our goal now is to try to find the equation of that line of intersection. We can use matrices to solve this system of equation, basically, and try to come up with a parametric equation of the line, or you can do this by inspection, noticing how pi 1 contains 2y term and pi 2 has an equation that contains a negative 2y term. So what we can do is to eliminate y and try to write x in terms of z using parameters. So let z be a parameter. Okay, and then write x and y in terms of z, or instead of z we can say z equals a lambda. Okay, we'll use lambda. So let's, based on what we said, if I add the two equations together, I'm gonna have 3x minus 9z 7 minus 10 minus 3 equals to 0. So x technically is 3z minus plus 1. Okay, when I rearrange the equation. And then, let's see. Now we have to find a way to write y in terms of z, the parameter. So we have to eliminate x. What we can do is we can multiply the first equation by 2 to line up the coefficients of x, so minus equation 2. So 2x minus 2x gone. 4y plus 2y, 6y. Negative 8z plus 5, negative 8, so minus 3z. 14, 24. Like that, okay? So next we're going to isolate 6y, 3z minus 24. Divide both sides by 6. I can factor 3 from the numerator, so z minus 8 over 2. Okay? So like we said, because we're going to let z be lambda, so that the line of intersection of the two planes will be x equals to 3 lambda plus 1. And then y is lambda minus 8 over 2, and z is equal to lambda, just like that. Okay. Let's take a look at example 2. So we're going to find the intersection of pi 1, pi 2. So n1 is 1, 4, negative 3, and 2 is 2, 8, negative 6, so 1, 4, negative 3. So indeed, I can write n2 as 2 and 1, which indicates that we have parallel planes. So if we have two parallel planes, the question is, are they coincidental? Okay, so let's see. Can I write pi 1 as a multiple of pi 2? Well, the constants 6 and 11, they don't differ by the ratio of 2. So that means pi 1 cannot be written as a multiple or scalar multiple of pi 2. For k belongs to real numbers, this indicates that the planes are not identical. Okay, as a result, there is no solution. So if you recall, what we are looking at here are two parallel but non-coincidental planes. Okay, pi 1, pi 2. Example 3. Find the Cartesian equation of the line that passes through 2, -1, and 7, and is parallel to the line of intersection of pi 1 and pi 2 given below. Okay, so that means we're looking for an equation of a line where we already know the position of it, but we need to know its direction vector. Since it is parallel to the line of intersection of the two planes given, that means by solving for this line of intersection, we can use its direction vector in order to find the line that we're truly looking for. Okay, so in this example, I'm going to demonstrate how we can use matrices to solve for the line. We could find it in parametric form. So here we go. I have 1, 2, -3, -6, 3, -1, 2, and 4. Okay, so we're looking for line of intersection in parametric form. If we're assuming that z will carry that parameter, that means that we need a relationship between x and z and y and z relationship. You know what? I shouldn't use that sign. Don't want you to confuse it with a subtraction. Okay? So because of that, I should eliminate y in one of these equations, and I should eliminate x in the other equation. Okay, so how can we do that? So let's do 3r1 minus r2 to eliminate x's. So I get 0, 3 times 2, 6, 7, -3 times 3, -9, minus 2, -11, -18 minus 4, -22. Okay, now remember we want to get rid of y in one of these equations. So what I can do is I can think about 2y and -y. So I can do maybe r1 in the first matrix and then add 2r2. Okay, because that way 2 in the y column, 2 minus 2 is 0. Okay, so r1 is 1 plus 3 times 2 is 6. This is 7. -3 plus 2 times 2 is 4 is +1. -6 plus 8 is 2. Okay, so effectively I have found 7x plus z equals to 2, or x must equal to 2 minus z over 7. Okay, and then second equation, I have 7y minus 11z equals to -22. So y is 11z minus 22 over 7. Well, since both of these parameters have a fraction of 7, what I can choose, instead of z being lambda, I can use z equals to 7 lambda. then x will be 2 over 7 minus 7 lambda over 7, which is lambda. Y would be 11 z times, well, so z is 7, so 77 divided by 7, so 11 lambda, and then minus 22 over 7 like that, and then obviously z is going to be 7 lambda. Okay, so this is the parametric form of the line of intersection. All right, and of course we can convert this into vector form or vector equation, because that will be easier for us to read off the direction vector that we're looking for. So its vector equation will be 2 over 7, negative 22 over 7 and 0, plus lambda times negative 1, 11, and 7. Okay, so now we're ready to actually find or state the line that we're looking for. Okay, so the line that we're looking for is now 2, negative 1, 7 plus, let's call its parameter s, negative 1, 11, 7, having the same direction vector as our line of intersection. Okay, we need to put this into Cartesian form. So one way of doing it is to first write out the parametric form and then isolate s the parameter. Okay, so here we have x equals to 2 minus s, y is negative 1 plus 11s, and z is 7 plus 7s, okay, which gives us s equals to 2 minus x in the first place. Okay, let me write this out. The Cartesian form is, okay, so s is 2 minus x equal to y plus 1 over 11 equals to isolating s in the z line, z minus 7 over 7. Okay, so, and this is what we're looking for. Okay, so now let's move on to take a look at intersection of 3 planes. So now things get a lot more interesting when we are trying to figure out how 3 planes can intersect. So looking at the diagrams here, if we have a consistent systems, meaning that we do have some sort of an intersection, 3 planes can, of course, intersect at a point. So like the corner is touching each other. And of course, you can imagine extending the planes further down, further into the page, and further to the left, okay? 3 planes can also intersect at a straight line. And then in case 2b, 2 of the 3 planes could be 2 identical planes, and they intersect with a third plane along a straight line. In case 3, all 3 planes are identical, so they have infinitely many planes, as their intersection. And then, of course, the 3 planes may not have a consistent system, meaning that, they don't share a common line, a common point. It could be, 2 of the planes intersect, but not all 3. So it's kind of have this like triangular prism idea. Okay, so only 2 planes intersect at a line at a time. Or if you have 2 parallel planes, they can intersect a third plane, or all 3 planes are parallel to each other, so they are not coincident. Nothing is, coincident. Or 2 are the same, parallel to the third one. So once again, these are inconsistent systems. All right. In terms of solving systems of equations, But then from the type of solutions that we get, we can interpret, give them a geometrical meaning based on what we saw in those diagrams, okay? The most organized way to solve these system of equations, of course, is by using matrices. So I'm going to turn this system of equation into an augmented matrix, 1, 3, 2, and 5, 2, -1, -4, 4, 4, -3, 1, -3. Okay. Using elimination, I'm going to keep my first line the same, 1, 3, 2, 5. I need to eliminate the first entry in the second row. So 2R1 minus R2, that's 0, 6, 7, 4, 8, 5, 10, minus 4, 6. Okay, and then I can line up coefficient of 4. So 4R1 minus R3, that will be 0. Okay, I have 12, 15, 2 times 4, 8, 7, and then 20, 23. Okay, next, let's eliminate the middle entry in the last row. Okay, so copying 1, 3, 2, 5, 0, 7, 8, 6. Okay, so I gotta, these are big numbers. So 15R2 minus 7R3 is what I need. When I do that, I get 0, I get 0. So now 8 times 15 minus 7 times 7, just use a calculator. This is 71, and 6 times 15 minus 7 times 23, I got -71. Okay, and so of course I can make my number smaller. In row 3, if I divide both entries by 71. Okay, so 0, 0, 1, -1. This is definitely a lot easier to use. I'm going to use Gauss-Jordan method, meaning that I want the diagonal to be 1s and all 0 entries otherwise. Okay, so that means R2 minus 8 R3 is what I need here, and R1 eliminating the 2 to R3. Okay, so 1, 3, 0, and then 5 minus 2 times -1, so 7. 1, 3, 0, 7. Okay, so R2, 0 minus 0, 7 minus 0, 8 minus 8, so 6 minus 8, so 6 plus 8, 14. All right, keep going. Okay, second row, I can definitely make the number smaller by multiplying R2 by 7, so 0, 1, 0, 2, 0, 0, 1, -1, 1, 3, 0, 7. Do I have room? Okay, I should be able to finish this on the next row. Okay, I need to eliminate the 3 in the first row, so R1 minus 3, R2, it is. Okay, let's see. R1, 3 minus 3, 0, 0 minus 0, 7 minus 6 is 1. Very well. Okay, so we have successfully used Gauss-Jordan to solve the system of equation that leads to, obviously, x equals to 1, y equals to 2, and z equals to -1, resulting in a point of intersection of the 3 planes is 1, 2, -1. And here is the diagram showing, schematically how the 3 planes can intersect at this point. Just like that. Okay? System of equation B. So here are 3 planes. Let's check whether they're parallel or not. So N1 is 1, 3, 2. N2, normal, is 2, -1, -4. normal 3 and 3 is 5, 1, negative 6. Can I write these as scalar multiples of each other? Nope, so they are not parallel. The planes are not parallel. Okay, so let's try to solve this then. 1, 3, 2, 5, 2, negative 1, negative 4, 4, 5, 1, negative 6, 13. Okay. So notice how the first two lines are actually the same as, or first two planes are the same as the ones in part A. Okay. So that can help us to speed up our work a little bit, because I know in the second step, I'm going to result in the same line as the last example. That would be 0, 7, 8, and 6. But then for the third line, we still have to work that out. 5R1 minus R3. Let's see, that will be gone. So 15 minus 1, 14. 10 plus 6, 16. 25 minus 13 is 12. All right, so I guess keep going. But I do notice something here. When you compare the second row and the third row is basically twice of the second row. Okay. So what happens if I follow, the typical steps to try and eliminate the y in the third row now? So this is 2R2 minus R3, which results in a bunch of zeros, okay? What this implies also is that, like, if I take 0z equals to 0 from the last line, well, this is always true. Right. So this implies that there will be some sort of intersection. It will be a line. So we're going to use parameters. Okay. In this case, we can say that the first equation from the matrix is x plus 3y plus 2z equals to 5. And then second equation is 7y plus 8z equals to 6, and 0z equals to 0 is that. And if we let z to be lambda, when we sub it into equation 2, we can write y in terms of lambda, right? So we have 7y equals to 6 minus 8 lambda, or y is equal to 6 minus 8 lambda over 7. All right. And then I need more room, I think. Oh no, I still have room. Now let's substitute y equals to 6 minus 8 lambda over 7 and z equals to lambda into equation 1. Okay. We have x plus 3y plus 2z is now lambda equals to 5. All right, so what have we got here? I have x plus 18 over 7 minus 24 over 7 plus 14. 24 plus 14. 10 minus 10 lambda over 7 equals to 5. Or 5 times 7 is 35. 35 minus 18 is 17, is it? Yeah. So I have x equals to 10 lambda over 7, and then plus 17 over 7, like that. All right. So what does this imply? This implies that we have, let's go to the slide here. This implies that there is a line of intersection. Which has the parametric equation of x equals to 10 lambda over 7 plus 17 over 7, y equals to 6 over 7. You know what? Let me write it in order. Okay, and this line of intersection we say has parameters x equals to 17 over 7 plus 10 lambda over 7, y equals 6 over 7 minus 8 over 7 lambda, and z equals to lambda. Okay, and then let's put the line in. The three planes will kind of like intersect in the middle, and then the line would be sitting right there. Okay, see if I can make it thicker. Okay, so like that. Moving on to part C. Here we have three planes again. N1, first normal, is 1, 3, 2. N2, second normal, is 2, 6, 4. Okay, right away, I see N1 and N2 are parallel to each other, right? So N2 can be written as 2 and 1. So that means plane 1 and plane 2, they are either parallel or coincidental. Okay, so that's based on the normals. But I cannot write plane 1 as a multiple of plane 2 because of 5 and 15, they are not multiples of 2, which means that they're not coincidental. Incidental. Okay, so that's our reasoning. But then, if I check N3, which is 5, 1, negative 6, this is not a scalar multiple of N1 or a scalar multiple of N2. So that means pi 3 is not parallel to pi 1 and pi 2. So as you can see on the side here then, pi 1, pi 2 are parallel, but pi 3 is not. So we have an inconsistent system. And that is, there is no solution. Okay. And of course, last but not least, let's examine one more possibility here. Okay, the diagram is already there, but let's show why that's the case. Okay. So N1 is 1, 3, 2. N2, normal 2, is 2, negative 1, negative 4, but not scalar multiple of N1. N3 is 5, 1, negative 6, also not a scalar multiple of anything. So this is not parallel. Okay, let's try to solve this then. 1, 3, 2, 5, 2, negative 1, negative 4, 4, 5, 1, negative 6, 8. Okay, let's see. 1, 3, 2, 5 is fine. 2R1 minus R2, that's 0, 6, 7, 4, 8, 10, minus 4, 6. Okay, 5R1 minus R3, I have 0, 15 minus 1, 14, 10 plus 6, 16, 5, 25 minus 8 is 17. Okay, so the second line and third line are not the same, so keep eliminating. Copying 1, 3, 2, 5, 0, 7, 8, 6. All right, so 2R2 minus R3 to eliminate the Y entry, so 0. I have 16 over 16, 0. 6 times 2, 12, minus 500. So this is saying 0z is equal to negative 5. Of course, this is not possible. This is impossible. Okay, so that means the planes, none of the planes are parallel to each other, but there's no solution, there's no any line or point of intersection. We must be thinking about the case where pairs of planes are intersect with each other, but none of these is a common line of intersection. So it's kind of like that prism setup in the middle here. Okay.